thanks to the organizers for inviting me here. Wolf gave me the task of introducing you to meteorites. Astrobiology is a pretty diverse field, and from talking to some of you here, I realized that it's even more diverse than I thought it was. So a lot of you probably don't know a whole lot about meteorites, so let me give you some details here. Let me just take this recent event in Denmark to introduce you to it. This is a pretty dramatic picture, I think, which was taken in February where this huge fireball points straight down toward Copenhagen. I live on this side, and the museum where I work is on the other side, and you might think that nobody survived in Copenhagen. Unfortunately, it wasn't that bad, but we did actually have meteorites fall in the city. So meteorites are time capsules from the birth of the solar system. They far outdate the oldest rocks on Earth, and actually some of them date back to the birth of the solar system, containing particles that are as old as the solar system. Some of them come from molten asteroids also, so there's quite a variety of different types of meteorites and can tell different stories about how the solar system formed. So let me just show you this, which is kind of interesting. Here's a picture again. This is a picture taken from the Austrian Alps, 900 kilometers from the fireball. And those of you on the first row might see the fireball here. I can enlarge it a bit. Here it is. This is taken from 900 kilometers away. And there's even, if the video, yeah, that works as well. Here's a video that shows the fireball going down toward Copenhagen. That was taken from the west coast of Denmark because, as you might see here, there were actually clouds over Zealand, so we couldn't see it from the city itself. Based on the observations, we were able to track the meteorite from about 80 kilometers above the ground down to 20. And you can then plot the route. Came from the southwest and headed toward Copenhagen. And since we have the video of the velocity information and we have bearings, or we have pictures from different directions, we can reconstruct the trajectory and back calculate to get an orbit around the sun. And we can also forward calculate to see where it landed. And here's actually one of the first pieces that were found on the day after, a 60-gram meteorite. Most of it melted on its way down. That's why it's such a dramatic event. But below this fusion crutch, which is about 0.1 millimeter thick, it remained cold. So inside the meteorite, even though most of the stuff melted away, inside it, below the crust, you find material which is unaltered since the birth of the solar system. The reason why it's not hot all the way in here is that it only lasts a few seconds. So even though it's like 2,000 degrees on the surface, the heat doesn't penetrate to the interior in those few seconds, which is fantastic because all of the information preserved since the birth of the solar system would, of course, have been destroyed if we allowed it to heat to the melting point. So, meteorite basics. Meteorites sample the early disk around the sun that we've seen pictures of this morning. Dust and particles orbiting the young sun later accreted to form planets. A lot of it did, but part of it accreted to form small asteroids like this one, which is Gasper, that you've probably seen before. And asteroids are then subsequently eroded or even sometimes destroyed in collisions. You can see craters on the surface of this. So pieces are knocked off, start their own orbital evolution, and if we are lucky enough, they might fall on Earth like this meteorite, and we can cut through it and find particles that date back to this phase. So these particles that actually formed from the birth of the solar system and during the first few million years can be used to reconstruct what's happened up here. So they give us access to actual physical samples that date back to the birth of the solar system. Other asteroids melted so that the metal drained down and formed a central core, and we had also silicate melting that created a volcanic crust. So we get bodies that resemble the Earth. I'm not going to talk too much about that. I'll mainly focus on these guys over here. So what can they tell us? Well, they can actually say a little bit more than just how the solar system formed. They can also provide some information about the stellar sources that provided material for the solar system. So here's again Orion. We've seen it a couple of times before. This is a stellar nursery where a molecular cloud Yeah, so stars in our vicinity provided matter for the solar system, and the meteorites can actually tell us something about the types of stars that were in our surroundings and died just before the solar system. We can, of course, also date the solar system, but we can actually do more than that. We can date different particles and then track the first few million years of the solar system from the time when formed up to the time when the first kilometer-sized small bodies formed. And of course, they are also bulk samples of solar system matter, so they can tell us something about the chemistry, not just the elemental abundances, but also about some of the organics or the molecules in the early solar system. We also try to put this into something like these models that we've also seen before. When we talk about the inner solar system, we think about the innermost few astronomical units, whereas when astronomers talk, they talk about the innermost 50 astronomical units, because that's pretty much what you can resolve in astronomy. So I've realized that there's a bit of a difference in terminology there. But most of these, we want to try and put these particles into a context in the early solar system. First, let's talk a little bit about the stellar sources. The reason why we can say something about the stellar sources to our solar system is that we have short-lived radionuclides in meteorites. Here's a list of them. Their half-lives are measured in millions of years, which may not seem short-lived to you, but the reason why we call them that is that they are now extinct. 4.5 billion years later, there's nothing left, or at least no detectable amounts. We can detect them in meteorites, and their presence in meteorites tell us that they must have been synthesized shortly before the solar system formed. Otherwise, they would have decayed away. And there are various potential sources, supernova, SN, or various types of stars, or in some cases, they could also form within the solar system by particle irradiation. I'm going to talk a little bit, or mainly about aluminum-26, which is a particular interesting short-lived isotope. So aluminum-26 is primarily produced in supernovae. So we know that there were supernovae somewhere in the vicinity, in the cloud, that contributed matter to the clouds from which the solar system formed. We can measure the abundance of aluminum-26 in the early solar system. And the abundance turns out that for every 1 million aluminum-27 atoms, which is sort of the regular aluminum variation you can buy in the hardware store, for each million of those, you have 50 aluminum-26. So it doesn't seem like a whole lot, maybe, but it's actually quite significant. Because decay of that amount of aluminum-26 can heat an asteroid by up to 6,000 degrees. So it's a very potential heat source. It's, of course, also a chronometer, because it decays rapidly. So under some assumptions, you can actually use it as a chronometer. And of course, it causes melting of asteroids that formed within the first million years. And since we do actually have plenty of asteroids, like the ones I showed before, from which you get iron meteorites, this is a piece of an iron meteorite that came from the core of such an asteroid, we know that these melted asteroids existed, so we know that asteroids had grown to kilometer-sized within the first 1 million year of the solar system. So how can you detect something that's not there anymore? It decays within the first few million years, like 6 million years, and it's gone, as you can see here, from its initial abundance. It decays to magnesium-26. So here on Earth, we have magnesium in 3 variations, 24, 5, and 6. And part of that 26 is a product of decay of aluminum-26. And the trick is that if you have a very mineral which is very rich in aluminum, and therefore, if it formed early, it must have had a lot of aluminum-26. And those minerals, you tend to see an excess of magnesium-26. So it's correlated with the abundance of aluminum. And the only reasonable assumption is that this is due to decay of aluminum-26. So we can actually detect it, even though it's not there anymore. It used to be a bit controversial, this thing about having aluminum-26 that formed in a supernova, because you tend to think about supernova as pretty destructive things that shouldn't be associated with birth of solar systems. But in this model, which has been done by some of my colleagues at the museum, they tracked the evolution of a giant molecular cloud with star formation, production of aluminum-26 and decay of aluminum-26 and ejection of matter into the cloud. And you can see if you start out with a low abundance and then you let the cloud live for a while, you increase the amount of aluminum-26 and you quickly increase it actually above this hatch line, which is the level that we see evidence of in the early solar system. So this is just an example of us living or having formed in an environment where there were also massive stars that contributed to the dynamics of the molecular cloud. So let's dive into these chondrites. Each chondrite contains millions of particles that were sampled randomly in this disk. And here's, of course, this cartoon showing the disk. So each particle here has its own history. It's not like picking up a piece of granite where each mineral comes from the same place and formed at the same time. Each particle has its own history. So there's quite a bit of information in this. If you look at it closer, you can see these little round objects that we call chondrules, thus the name chondrites. You can see how thin the fusion crust is. And below this is pretty much undisturbed matter from the birth of the solar system. There's also a lot of fine-grained material, which is usually overlooked because it's just fine-grained and black and looks kind of dull. But right here, it's actually very interesting because it's in the fine-grained material that you find the volatiles and the organics. So we'll get back to that. If you put it in, look at it in thin slices of these meteorites, you can see these little round things that were actually once molten droplets. So you took fine-grained material in the disk orbiting the young sun, melted it to form these droplets that then solidified freely orbiting around the sun. So those are chondrules. The other things that you see dominating in the chondrite are these CAIs, calcium aluminum rich inclusions. And the reason why they're rich in calcium and aluminum is that those are the elements that condense out earliest. If you take a gas of solar composition and cool it down, then the first minerals that form, they are rich in calcium and aluminum, and thus also quite useful in terms of constraining the abundance of aluminum-26. So these are condensates formed at very high temperatures, and these were examples of something that got melted. So, and both of them, of course, thermally processed. Of course, you also you tend to look at them individually, but if you look at the meteorite as a whole, here's an example of that. Meteorite which is loaded with chondrules. And earlier today we heard that in order to understand planetary formation, you have to solve the dust problem. And one provocative answer to that is, well, there was no dust, because clearly when you look at that, there is no fine-grained material. Some bodies actually grew in the absence of dust because it all been transformed into these chondrules that are millimeter-sized. You can see a little bit of fine-grained material, but we're looking at a few percent, and part of that is actually in the form of mantles of these chondrules. So dust was not everywhere when bodies started to accrete. Some of my colleagues at the museum have spent a lot of time dating these things and have succeeded in dating these tiny entities, the chondrules and the CAIs. And they use not the short-lived isotopes that I talked about before, but long-lived isotopes like uranium-235 and 238 that are still present today. And because they're still present, you can use them to do absolute ages. And what they find is intriguing. The CAIs, the first condensates out of the hot gas, formed 4,567.3 million years ago, actually in a very narrow time window suggested by aluminum-26 evidence. So they formed at the birth of the solar system. And chondrules, the other things that you see here, they formed over several million years. And sometimes you find objects in a chondrite that formed several million years apart that apparently somehow survived out there before they finally accreted to the same body. So you had particles that stayed out there, that didn't just immediately drift into the young sun. Let's look at the CAIs in a little bit more detail and some other ones, also high temperature condensates. Here's one of those. This is an elemental map where calcium is in green and aluminum is in blue. So these are calcium aluminum rich inclusions. You can see there's a lot of green and blue. First, the blue stuff condensed at high temperature, and then as the temperature dropped a bit. So yeah, so this is a bit of a condensation sequence from high temperatures to lower temperatures. Some of them got remelted and formed something that actually sort of resemble chondrules. So you're taking one of these, remelted it to form a round object, but it's still rich in calcium and aluminum. Chondrites are surprisingly diverse. You might think when you look at this and you know that things are drifting in and we know that things got kicked out, that this is sort of, it's a really efficient way of just messing up things, and all that dust would tend to look the same. But when you look at them, even those of you, and there are quite a few that are not geologists, you'd probably realize that these are not very similar. This is an example of something that formed in a reduced, dust-free environment. So there's a lot of metallic iron. The white, shiny stuff you see here is actually metallic iron, probably formed fairly close to the sun. Whereas this one, a carbonaceous chondrite, Murchison, that some of you may have heard about, is very rich in that fine-grained material that actually contains the organics. And has very little, it's very oxidized, so it has very little metal. You have to really look hard to see any metal at all. Of course, still a lot of iron, but it's oxidized. So, and that's probably related to the snowline, solids that accrete inside the snowline form silicates and metal. But if you're outside one of the snowlines, you also add ice. And there was clearly evidence of water and other types of ices in these guys that must have formed further out. There are many different types of meteorites. We're not going to go into that, but these are sort of the superclasses, intertype chondrites I choose. They are highly reduced. They have very few CAIs, and which is actually kind of peculiar because we think of the CAIs as something that formed close to the sun, as these guys did, but we don't see a whole lot of them in there. They have been thermally processed in the asteroid, which is a bit of a problem because we hope to see these chondrules and CAIs. They're examples of something that formed in the nebula, but of course they also have an asteroid history, and these asteroids tend to be heated somewhat. Ordinary chondrites, because 80% of all meteorites that fall are these, just like the one that just fell in Copenhagen. They're more oxidized, less metal, still few CAIs, and almost no matrix. You see, it's just chondrules everywhere, and also thermally processed. And then those that are maybe most interesting for us today, the carbonaceous chondrites, variable oxidation. CAIs are common, although they form far from the place where we think the CAIs formed, so things must have been thrown out. Abundant matrix loaded with organics, not so much thermal processing, but aqueous alteration, which require not just ice, but actually molten ice or water that reacted with these things and sometimes dissolved them partially. If you look at the abundance of these components, you can again see huge variations in abundance of matrix. The dark stuff here that don't look very interesting, but is actually loaded with organics. Whereas up here, there's very little of that. Here's a bunch of different types of meteorites. You don't have to be able to read that, but if you look at the different components, chondrules, for example, in blue, those are considered the main component of chondrites, but in some cases, they're actually not very abundant. The matrix in gray is what you guys are probably interested in, is very abundant in some types of meteorites, but not very abundant in others. So let's look at CM chondrites, which have heaps of matrix and were never heated very much. There was another famous example. We've been quite blessed with meteorites in Denmark. This one fell in 2009, and that was a CM chondrite, a very interesting type of meteorite that was seen flying on a surveillance camera in Sweden. They thought it fell in Sweden, but fortunately it made it across the border and fell in Denmark. So, and only 25 grams of it, but it's amazing what you can do with a little bit of material. So here's again a thin section showing all the matrix material, lots of chondrules, a CAI down here, lots of interesting stuff. Look at it closer, you see the chondrules. Here's a molten chondrule that collided with another molten chondrule that glued onto it here. So you know that where these chondrules formed, there were lots of them. Others failed to melt completely, so they're sort of grainy, like this one. And then the matrix material. The interesting thing about this one was that the guy that found it brought it into a summer house he'd rented in Denmark. He was a German guy. And an hour later, he realized it was stinking of something, some sort of organics that he thought he had spilled, until he realized that this was the meteorite that was smelling bad from the organics, because this was the first time it had been heated to 20 degrees centigrade for 4.5 billion years, and it was oozing out the stuff that it's gathered in the solar system 4.5 billion years ago. So fortunately, it didn't ooze out all of it. We sent 0.1 gram to Philip Smith-Copland's lab in Munich. He has a nice machine here that can analyze organics. He found 24,300 mass signals, corresponding to about 7,000 different types of organic compositions. Interesting enough, it turns out that Maribo here is different from another CM chondrite, Murchison. Of course, you'd like to relate this straight back to the observations that you can do in interstellar clouds, but there's probably a few steps involved before you get to the meteorite. It's been processed in the early solar system, and it's been accreted onto the asteroid, where it was heated and there was aqueous alteration, and that may have been a little different on these two, although we think they came from the same asteroid. And then finally, Murchison fell in Australia in '69, and it's been sitting there in a fairly hot environment, and I think also things change for some of these species along the way. So that may be part of the reason why we see things that are unique to Maribo, things that are unique to Murchison, opposite actually, and things that they have in common. But lots of information on organics in these, including the amino acids. Another thing we know about this Maribo is that we also determined its orbit, and here it is. I apologize, this is in Danish. I didn't have that in English. But you can probably recognize the terrestrial planets here. So it took a huge dive inside Mercury and almost out to Jupiter out here, and of course crossed the Earth. It's a very eccentric orbit. If you're not familiar with that, this plot shows you the distance from the Sun and the eccentricity. And asteroids marked in black tend to have low eccentricities. They are in fairly circular orbits. Various cometary bodies have eccentric orbit. This is the red is called Maribo, and there is Comet Inge and the Torids, which are believed to be associated with Comet Inge. So that hints toward a cometary origin. Another thing is that when you look inside it, you see these objects that are things that have been dissolved in water. It's something called tachylinite. So at an early stage, early in the solar system, something was dissolved in water and then precipitated out here. And this may be hard to see, but outside it, you have a fine-grained rim of dust. So apparently this piece was processed in a place where there was access to water, hot water, dissolved material, and it was kicked back out into the nebula, acquired a dust rim, and then landed in this Maribo meteorite approximately 4.5 billion years ago. Almost there. And that leads us to the last figure I have, which is the question of where the Earth's water come from. You may know that there are two competing theories. We accreted inside the snow line, so there really shouldn't be any water here. So it could have come from comets, or it could have come from carbonaceous chondrites. And the way to measure this is to look at the D to H ratio. So far, comets seem to have different D to H ratios than the Earth water plotted over here. There's only one comet that seemed to plot at the ocean line. Recently, Rosetta brought back data, and there was a hope that this would also plot on the line, but of course it plots way above that. But carbonaceous chondrites seem to have water that have roughly the right D to H ratio, which suggests that the water came from the asteroid belt, or the outer asteroid belt where carbonaceous chondrites seem to originate from. Okay, so in summary, we can find chondrules and CAIs that formed within the first few million years after T0, so we can reconstruct in some detail the evolution from the birth of the solar system up to the point where the first kilometer-sized body is formed. Through short-lived radioactive isotopes, we can constrain the surroundings, or the types of stars that surrounded us when the solar system formed. We can see that at least some bodies accreted in the absence of dust. And carbonaceous chondrites, particular interest here, they contain water similar to the water on Earth, and they contained, they delivered a variety of organic molecules to the Earth when life originated on Earth. I guess I skipped that one. And then I can't just help pulling off a commercial here. We have an origins course, which is very appropriate for this cost action, that describe the whole process from the Big Bang up till 2013 when we launched the course. So it tells you about evolution of life on Earth, but also how solar system formed. You can check it out, it's free, and you can join the 80,000 students from 187 countries that have enrolled in this course so far. And there are more details on meteorites and that. Thank you.